Welcome to Black Hat 2015. Now it's a little late in the afternoon, but we got a good speaker here for you. Once again, if you haven't shut up your cell phones already, please do so now. And without further ado, I'd like to welcome you to Mandalay Bay BD. This is Optimized Fuzzing IOKit in iOS. Please welcome Lei Long.
Thank you. Good afternoon, everyone. My talk is Optimized Fuzzing IOKit in iOS. My name is Long Lei. I'm a security expert in mobile security of Alibaba Group. And now I am focused on security research of iOS. In my presentation, first is the introduction of our work, and then a dynamic approach to export information about IOKit classes is given now. And this is the key point of my presentation. And then, based on the extracted information, we also craft an application to fast IOKit in iOS. And at last, I will show several vulnerabilities as a result. Now the introduction. In iOS, IOKit is the bridge to connect user space and kernel. And also the IOKit is the foundation to construct and link a kernel extension. So the information extracting of IOKit in kernel extension is crucial to fast IOKit in iOS. In previous research, information extraction is mainly focused on IO external method dispatch and relies on status IDA analyze. However, it has several disadvantages. First, it requires as method symbols, but as method symbols have been removed from kernel cache since iOS 7. And also it requires a decrypted kernel cache. But even with decrypted kernel cache, there are still a lot of instructions cannot be resolved in the IDA. And even worse, the extracted information is insufficient. And now our work is based on dynamically kernel read and write, and we can extract not only IO external method dispatch, but also IO external method and a series of runtime information. And what's more, we are independent of as method symbols and decrypted kernel cache. And more sufficient information can be obtained. Before our work, there are two prerequisites listed here. You need a jailbroken device and task for PID 0 kernel patch. Let's begin with information extraction. In this chapter, I will introduce how to extract the useful information about IOKit in kernel and kernel extensions. There are 4 parts. The first part, basic information of all OS object subclasses, and then how to access to a specific user client, and third, our external method dispatch, and fourth, our external method. Well, the last two is used for parameter check in kernel. Now the first part of information extraction, basic information. The first question is, what is the basic information? It is the information of all OS object subclasses, and it includes class name, vtable star address, virtual method, and its vtable offset, symbols of overwritten virtual methods, instance size, and inheritance relationships. Here we take a class for example. The class name is Apple ARM PMU power source, and the bundle ID in blue, Commodore Apple driver ARM platform, and the vtable starting address in green, instance size in yellow, and the inheritance relationships in red from OS object to IOPM power source. And the last is vtable offset and virtual methods. Now the second question is why we need the basic information. First, we can use it as a quick search to accelerate kernel analysis. And then it's a necessary foundation for analyzing kernel without a decrypted kernel cache. But even with a decrypted kernel cache, there are still a lot of instructions cannot be resolved in the IDA. You can see like that. Basic information can fix it, but the vtable data. And then we can obtain the service provided by kernel extension, and the instance size can be used in vulnerabilities exploiting. Now, how can we extract the basic information? First, we need to locate all match-alls data constant sessions in both kernel and kernel extensions, because vtable data is within these sessions. And then we need to pick out the vtable data from these sessions because, by its layouts and characteristics. Now the vtable layout. Vtable is a series of continuous some virtual methods address. So the address must be in the range of text segment or pre-linked text segment. And there are at least 14 continuous address because OS object has 14 virtual methods. And at last, the number 0 virtual method is following at least 4 or 0 bytes. And now the vtable's characteristic. The most important characteristic of vtable is the get method class. The overwritten get method class returns a OS method class pointer, and the OS method class pointer is the key to get the runtime information. So if we can identify the get method class address, then vtable is filtered out. Next, I will introduce how can we identify a get method class address. Look at the definition of get method class. It defines in OS define method class and structures macro. So the implementation of get method class in different classes is totally the same, which is the foundation to dynamically resolve and identify this function. And then inside implementation, G method class is the key to get runtime information. Next, I will introduce how can we resolve the G method class in kernel and kernel extensions. Okay. Here is the instructions of get method class in kernel and kernel extensions. They have a little different, but we still can resolve the G method class by the equation in green. After locating G method class address, next is using it to get the runtime information. In G method class layout, what we concern with is superclass length, class name, and class size with the offset A, C, and 10. Sorry. Now we continue to resolve this variable. First is class name. Class name is an OS symbol pointer, and in OS symbol layout, it defines length and string, and they can form a while class name together. And the class size is an unsigned int. The superclass link is an OS meta class pointer. So we can use it transfer backwards to OS object, and we can get all the inheritance relationships. By now, we can pick out all vtable data by identifying get meta class, but we still need to know whether the kernel extension can provide some specific service or not. For example, in order to provide the service of IOKit set set properties, the kernel extension's service need to override set properties because the default implementation of set properties in SNU is totally empty. So we are concerned is some specific interface is overwritten or not. Here we identify overwriting by the virtual method address if the address is in the range of text segment. Then without overwriting, if not, then be overwritten. But it's not enough. Let's continue to get the symbols of overwritten methods. Now is the detailed steps. First, we make an abstraction. The names and sequence in same iOS version are the same in different devices. And then we pick out a device with decrypted kernel cache to obtain the names and sequence. So we can deduce the symbolization for those without decrypted kernel cache. But how can we obtain the names and sequence from decrypted kernel cache? Here's the detailed steps. First, we use command kernel cache to obtain the names and address pair. And then the vtable data we already obtained in our basic information extraction. At last, through the name address pair matching, we can get a sequence and names. By now, we can get the basic information of all OS object subclasses. Now, the second part of information extraction. How can we access to a specific user client? By now, we can get all OS object subclasses, surely including all IO user client subclasses. And now we need to access to this user client. For example, in order to access to IOPKE accelerate user client, we need a service name Apple Samsung PKE and the open type 0. But how can we obtain this information? Here is our approach to access to a specific user client. First, input the service name S1. And then after IO object copy class operation, we get the service name S2. And we try a lot of open type in a limit scope. If a client is open successfully, then we retrieve the client name C1 in kernel through the client MAC port and client address. Now the triple C1 S2 open type is the access info we want to export. So with the access info, we can access to a specific user client. And now the detailed steps. First, we obtain all service name as S1, but OS KEST load KEST in Ford expand the same as 8.1.3, so we can't get the service name directly. But we can get them in our basic information extraction. And then we try all the open types from 0 to FF, as most clients use these open types. In a few open type out of this scope, we need to locate the overwritten new user client address and then to analyze it to get the open types. At last, we retrieve the client name C1 in kernel, but macport k object is also banned the same out as 8.1.3. Here we define another interface, macport space info, to retrieve it. Unfortunately, we can get the client address directly by using macport space info, as instead we can get the IPC port pointer. And here's the detailed steps. After connect to a client, we can use macport space info to get the IPC info name table in the current process. And then we compare each IIM name with the client port name. If equal, then the corresponding IIM object is the obfuscated IPC port pointer. Since the address is obfuscated, we still need to use VM kernel EPROM to subtract it. VM kernel EPROM is a global variable and used many times in kernel. Next, I will introduce how to get the VM kernel EPROM and the real IPC port pointer. Here, luckily, we define a function while virtual. It uses a Unix string and VM kernel EPROM macro, so we can locate the VM kernel EPROM address by locating the Unix string address. After locating the VM kernel EPROM address, we can finally get the IPC port pointer. And next, I will introduce how can we retrieve the client name via IPC port pointer. In IPC port structure, the kdata kobject field at the offset 14.4 is the client address. And then we retrieve the client name while the client address using the approach in our basic information extraction. First, get the vtable address, and then locate the get method class address, and then g method class pointer, and finally we get the client name. So by now we can get all triple access info. So with the access info, we can access to a specific user client. The third part of information extraction, IO external method dispatch. In kernel extension, driver overrides external methods to provide service to user model. And the overwritten interface provide our external method dispatch to their base class for the parameter check and function dispatch. If the actual parameter does not pass the IO external method dispatch check, then a E402C2 error will be returned by kernel. So IO external method dispatch is very important for our fuzzing parameter generation. How can we extract the IO external method dispatch? Here's the 4 steps. First, we narrow and determine the searching scope. And then we match the IO external method dispatch table's characteristic in the searching scope. So we can locate the IO external method dispatch table's starting address. And then we dump the whole table. First is the IO external dispatch table's characteristic. In a IO external method dispatch structure, it has 5 fields. The first is function. So the function should be in the range of text segment or prelim text segment. And the other 4 used to define the data length of integer or structure. So they should be in the range from 0 to FF. Or AF means any length is okay. And then we make the table length should be greater than 2 to make the characteristic more stronger. So with the characteristic, we can identify and adjust whether it is the dispatch table's starting address or not. Here's the detailed step to dump a dispatch table. On the left is dispatch table and vtable layout of most clients. First, we already obtained the client vtable in our basic information extraction. And after all continuous, all 0 bytes is client method class vtable also end with 0 bytes. So we can locate the position S. The position S is at the end of the method class vtable. And then we search from position S by byte to match the characteristic. If at least 2 continuous blocks matching the characteristic are found, then the first block starting address is the dispatch table starting address. And then we look to dump the whole table and stop if one block does not match the characteristic. As most clients' dispatch table can be dumped in the above approach, here's the complemental mechanism for those unavailable. First, we locate the overwritten external methods, and then we resolve all the LDR electoral instruction in these methods. And we check each corresponding address whether it is the dispatch table starting address or not. If yes, we dump the table. The 4 paths of information extraction are external methods. IO external method is a structure similar with our external method dispatch. When client overrides get, target, and method for index to provide service, it provides our external method to parameter check and function dispatch, and also a E402C2 error will return by kernel if check failed. And how can we extract our external method? Different from our external method dispatch, we can export our external method by directly invoking get, target, and method for index. We're using the arbitrary kernel code execution to invoke the get, target, and method for index. First, we use message out of line data as a carrier, and we need to locate the out of line data we create. First is the MAC port space info, and then to IPC MQ, to message, to IKM base, to IKM header, and to MSGH remote port. The MSGH remote port is the out of line data starting address. In RSA, the out of line data's metadata field has 15 bytes. And now I will introduce how can we use out of line data as a carrier to invoke get, target, and method for index. First, we craft a gadget client instance. and set its vtable pointing to the fake vtable data in our offline data. And then the fake get external trap for index points to return index ARM instruction in kernel text. Before invoking, we set the payload in 8 bytes. The first 4 bytes pointing to the target client A, and the last 4 bytes pointing to the target client A's get target and method for index. And then we use IOConnect trap tool to get the IO external methods address. Here's the parameters. We set the connect to the gadget client's MAC port. And the index is the payload starting address in our offline data. P1 is a writable kernel address in our offline data. And P2 is the IO external method table index. So we can get the whole IO external method table by calling IOConnect trap tool with different indexes. But now, all the contents of information extraction is given now. And next is use the information to craft our fuzzing application. Here is our fuzzing application's architecture. It is based on iOS launch daemon, so it can be invoked by OS on device booking. And then it includes first the panic log corrector. It corrects the panic log with the corresponding fuzzing parameter. And then the Springboard auto unlock. It unlocks the device automatically when device booking. The deadlock monitor and slow monitor used for improve the fuzzing activity. And the whole system can be run without humans interaction. Before we fuzz, we still need to know which interface is available in the target client. Here's the fuzzing elements. If the client overwriting client memory for type, then we can fuzz IOConnect MAC memory. If the client overwriting one of external method, get target and method for index, or get external method for index, then we can fuzz IOConnect call method. If the client overwriting set properties, then we can fuzz IOConnect set properties. If the client overwriting one of get target and trap for index or get external trap for index, then we can fuzz IOConnect trap. And also, we need to identify the unavailable interface to avoid low fuzzing activity and frequently and useless panic. Here we record 3 kinds of unavailable interface. First is invisible panic interface, and deadlock interface, slowly processing interface. Now we can do the real fuzz. In the research, we discovered that a lot of interfaces are dependent in the invoking sequence. So we call the selector in a random sequence to avoid dependence. And what's more, some other interfaces, such as properties, memory map, and trap, we also add into the fuzz randomly. Another discovery is that some clients don't finish its initialization before we fuzz, which caused the fuzz totally useless. Here we do find a way to solve this problem. We dynamically inject the fuzzing application into system process. And then we use MacPort space info to retrieve the client MacPort which already finished the initialization. So we can fuzz it. After fuzz is our experimental results. Here's the experimental setup. We test on iPhone 4S and with the iOS 8.1.2. And next, I will show two vulnerabilities as result sample. The first one, function free in IO data queue. Inside the implementation, queue size can be modified in user model, and it will be passed to IO3 align directory without any check. And then in Highland Park audio device user clients, client memory for type. When type is 14.4, then it will create a IO data queue to share memory with user client. So it may cause the buffer in KLOK June 4096 can be released into bigger KLOK June. Well, it's a typical buffer overflow vulnerabilities. It can cause two kinds of panics. The first one, unavailable address to read and write to, and free June elements has been modified. However, this bug has been fixed in iOS 8.3. And the second one, in the implementation of our resource set properties, it can accept any key and set the key to its properties table. And our resource is inherited from our service. And then in the implementation of new user clients, if the service properties table have the key, GIO user client class key, then it will use for the client's allocation. So the question is, if we set the key to our resource, then what happens? Then our resource can be bound to any client as a service. And so it's an interesting attack surface, and we can fuzz it with a lot of clients interface. Thank you. My presentation ends here, and this presentation, you can take away an information extraction approach to extract useful information about IOKit in kernel and effective fuzzing framework and tool vulnerabilities sharing. Thank you. You can ask any question with me offline.